Any better? Okay. So, so this is going to be the agenda for my talk. I'm going to present an overview of HPC on AWS and kind of the state of the art of how people do HPC with our offerings. What EFA is, and kind of give a quick deep dive on the different components of EFA, right from the kernel all the way up to the MPI stack. And kind of the road ahead and next steps and where we want to take EFA from what we have today. So HPC on AWS, in typical Amazon fashion, instead of kind of diving into the different offerings, I just want to talk about some customer examples of how people actually do cool things with what we build. These are kind of the broad class of services we offer. I'm not going to get into each one of those, but like a typical HPC offering, we have storage, compute, network, orchestration tools. There's plenty of information about all of this on our web pages. Of course, we have a broad partner community where our services do not suffice for a particular need. Partners extend the capabilities or add values on top of it. We have ISVs like ANSYS, infrastructure partners, technology partners, and of course, consulting partners. But on to the cool part, we have people doing weather modeling. For example, this chart is showing scaling on one of our previous generation compute instance types, C4, with the WRF CONUS model. We have quite a few people running WRF. We also have people doing design and engineering. This is a really cool startup out of Denver called Boom. They're trying to enable supersonic travel, right? And they ran this model with about 200 million mesh shells. They were able to get like 6 times speed up, kind of scaling up on AWS. That was pretty cool. Material sciences, Western Digital has been running this massive simulation job on a single, like a million vCPU cluster. vCPU is our way of saying hyperthreads. So that's like a 500,000 physical cores that saved their simulation time from 20 to down to 8 hours. This is the coolest one. I could put like cute animal pictures in my slide without getting yelled at for it. But the Australian Museum Research Institute did this genome sequencing study where they sequenced about 3.2 billion base pairs, trying to figure out like the eating patterns of the koalas and like how not to make them an endangered species and how genome sequencing research can help longevity of koalas. That was another cool study. But so those are the cool things that customers do, which is always good to talk about. But I'm here to talk about EFA, what EFA is. But before I can do that, I should kind of give a 101 for how EC2 evolved over time and what EC2 can do today. So this, you can kind of broadly think of the architecture like in 2 parts, right? The hardware, which is the physical servers that host your virtual machines or your instances, and on the right have the software, which is your instance itself. On the hardware, we have some sort of processor, Intel, ARM, our own A1 processors, a bunch of physical memory. For example, our C5 Skylake-based instance type has about 196 gigabytes of memory. And then on that little box you see on the left is what we call our Nitro Card, which enables us to offer like NVMe-based block storage to our instances and TCPIP-based networking, what we call enhanced networking adapter ENA. So this is kind of the high-level architecture, right? But I'm not doing justice to what goes on behind the scenes. There's like a phenomenal talk from Anthony Ligori, who's a principal engineer that he gave last November. It's on YouTube. You can look it up. It goes into details of all the little boxes and how the wires connect. If you translate that into how people do HPC, this is kind of like the high-level stack, right? So we have the ENA driver in the kernel. It's a NetDev. You have the standard TCPIP stack. You have your pick your own favorite MPI stack, OpenMPI, MPitch, Intel MPI, and you run your application on top of it, right? So with this, before EFA, these are kind of the performance trends we are seeing, right? So on the left, I'm showing the multi-stream bandwidth of MPI using OSU MBWMR, the OSU benchmark suite. And I'm showing different generations of our compute instance types, starting from C3 all the way up to the Skylake-based C5N. So one thing to note, over time, we've continuously iterated over performance, right? Both from a bandwidth perspective on the right, MPI latency, we've been shaving off latency as we iterate through these generations. But note that C5N is a 100 gigabit offering that we announced at reInvent last year in November. So as we started creeping up into the 100 gigabit space, we started noticing that TCP was not really giving us what we wanted, and more so in the MPI context. With like in the packet processing space, we could use something like DPDK, and that was filling a void. But there was not a semantic match to what MPI was expecting out of these fabrics. So enter EFA. So the stack that I showed earlier with some more extra boxes. So EFA gets you two main things. One, OS bypass networking that HPC is intimately familiar with. That's my poor attempt at showing OS bypass. And then the other thing, which I'll talk about later down in my slides, is a new transport protocol called SRD, Scalable Reliable Datagrams, with its own unique characteristics that help efficiency of HPC applications. And for the rest of the talk, I'll kind of work my way up the stack, talking about the device, and then all the way up to the MPI implementation. So the same diagram from before, it looks just the same. Now the Nitro Card, in addition to the ENA device on an instance, you can also see an additional PCI Express device for EFA. So if you launch an instance with EFA enabled, I skipped a bunch of tutorial slides which talk about how you would launch an instance and request EFA. But once you launch an instance, this is what you would see. In addition to the ENA PCI device, you also see the EFA device, and you can see the EFA kernel module kind of picking that up. What this device uses behind the scenes is kind of the second benefit of EFA, Scalable Reliable Datagrams. It's a new protocol we have designed, keeping in mind AWS's unique data center design and our network characteristics, and kind of the usage we have from different kinds of workloads. It is implemented as part of our third generation Nitro chip, the adapter I showed in one of the earlier diagrams. So EFA, the kernel device, the EFA, the device, has the kernel driver which exposes SRD as a driver QP type using the RDMA subsystem. It's inspired by the InfiniBand RD reliable datagram semantics without really the drawbacks of RD, meaning there's no limit to the number of outstanding messages per queue pair context. But kind of the main key thing of SRD is we get out of order delivery of packets. If you kind of think about it, right, there's no real strict requirement of message ordering for most applications, and even when there's a need, you can implement it in the host. And kind of over the years, the processors and Intel, for example, has made it easier to have more efficient rerouting mechanisms that can be implemented in the host processor. So there's no reason to kind of push that requirement down to the neck. So this protocol effectively doesn't provide ordering guarantees on message boundaries. What that allows us to do is it allows us to take multiple paths over the network using ECMP, and we can do better congestion control behind the scenes. Again, if we have multiple kinds of workloads coming from different customers, so we can react quickly to like small network events, link failures, congestion coming from bad actors. And if you think about why reliable datagrams, so TCP and kind of tail latencies have had kind of this war, right? So more so in the context of MPI, where most like tightly bound iterative applications, if they're doing like a ghost cell exchange, if you're doing reliability in the host software, you're looking at like a floor of tens of milliseconds of retry timeouts. And being able to do that in the hardware allows us to do a lot more from just a reliability standpoint without having to tax the host software for it. So that's SRD. So this is a bit of a, you don't have to read through the whole thing. I'll leave it up in my slides for you to look at it later, but kind of compares TCP, IB, and SRD, kind of where we see the differences and why we did what we did with SRD. And this is an example of like handling link failures with SRD in a typical TCP case. You're kind of blocked until the link comes back. With SRD, we can take alternative routes through the ECMP paths without drastically impacting application performance. So talking about the boxes that I showed earlier, so the EFA kernel module, so it is currently a driver in the RDMA subsystem. It supports the standard UD queue pair type. We also added a scalable reliable datagram, the SRD driver QP type. Currently, RC queue pairs are not supported. and as a result, upper level protocols are not supported, but we believe we can emulate it in software. If we have requirements or feedback, that'll help us prioritize that work over some of the other things we want to do in the future. We have also written a libIB verbs provider for the user space stack in RDMA core, using which we are also going to extend the libfabric EFA provider that I'll talk about in a little bit. So the driver and the user space packages have been pushed up for review with the open source communities. Linux RDMA core, the kernel driver has been going through some iterations of reviews with Jason and Doug and others in the community. And Gal Pressman, who's sitting in the audience, is the author. If you have any questions, he'll be happy to answer them. Likewise, there's also a pull request out for the RDMA core libIB verbs stack. Moving up the stack, libIB verbs, we're going to upstream 2 providers. Eventually, we have a EFA core provider that directly talks to the kernel driver for control path and the NIC for the data path. It exposes 2 endpoint types, the FIEP RDM for reliable datagrams and FIEP DGram for unreliable datagrams. They're both unordered channels, and they both support the 8 kilobyte, around 8 kilobyte max message size. So the EFA provider does not support tag matching interfaces of libfabric. It just supports the send receive APIs. The RDM endpoint is the one that talks to the SRD pair type that I talked about, and the DGram one directly talks to the UDQ pair type. The thing to note is the SRD pair type is not limited by any flow limiters in the EC2 network, but the UDQ pair goes through like the typical flow limiter on a single endpoint. We've also implemented a couple other things in the provider, which could justify a talk in itself, but there's a notion of a memory registration cache in EFA. We've extended that and added support for what's called user fault FD, which is kind of a standard mechanism to deal with like cache invalidations and all. Our plan is to upstream that as a kind of a common utility component sometime soon. And then moving up the stack, in addition to the EFA provider, we have what's called the RxR utility provider. There are a couple of reasons why we did it this way. Given the data we had when we started out writing these providers, we needed a way to extend the core EFA provider's abilities to support tag matching and to support segmentation and reassembly and so on. So RxR currently supports the FIEP RDM endpoint type, talking to SRD driver Q pair type. With the driver, it implements packet reordering on the receive side, because the incoming packets are going to be unordered from SRD. We support tag matching that helps MPI libraries. Most MPI libraries today use the tag matching API of libfabric. So we add that in RxR. We have a segmentation and reassembly protocol for messages larger than the MTU size. And of course, we have some additional secondary capabilities in libfabric. And there are a couple more I have not listed here. But the idea is RxR is designed in a way that it's not tied to EFA, right? It's a generic utility provider that can layer, or it's intended to layer over other providers in the future as well. But this is not upstream yet. We're going to talk to Sean and the community to see what the best way to, or what is the final form this provider is going to take compared to some of the other utility providers that are out there. So with EFA and with that stack, this is what our performance looks like now. Same chart from before, but this is the red line shows the EFA number, and we're able to hit the 100 gigabit limit. And also on the latency side, we're able to shave a bunch of latency. And you can see we're not going to stop there. We're going to continue iterating on performance and improving both the bandwidth curve and the latencies. So using EFA, currently EFA is supported on 2 platforms, the C5N 18x large instance type, that's our compute optimized instance, and the P3DN 24x large, which is our GPU optimized instance type. It has 8 Tesla V100 GPUs. And then the kernel driver, while we continue to work with the upstream community to get the kernel driver upstreamed, we're also making the source available for anyone who wants to directly grab it. It's on our GitHub. Likewise, both the libfabric and the RDMA core stack, while we work to get that upstreamed, we're also going to make it available on GitHub repositories. until that whole stack is upstream through the first half of 2019, there's going to be a custom version with custom releases for the libfabric and the RDMA core stack. Moving up the stack, MPI and Nickel, one of the goals of EFA is to not just support MPI, but also other higher level programming interfaces for machine learning, like Nickel that Brian talked about yesterday. So OpenMPI 3.1.3 and above will be supported, and Nickel 2.3.8 or later will work with EFA. Intel MPA and MPIT support are in development. We found some quirks that we had to work through, but that's going to be our first priority after we launch, to get Intel MPA working on EFA. There is currently a limitation of one EFA ENI per EC2 instance. Then there's some additional information for how you can use EFA in that URL there. So that's kind of the internals of what goes into the EFA stack. Thinking of the road ahead, currently EFA is in customer preview. It should be generally available shortly. Like I said, kind of the biggest focus right now is to work with the different communities, folks who are here, right? That's why this workshop is so important. Kind of work with the community to get the different components upstream, reviewed, take feedback, and then iterate over those. Depending on how the kernel module and the Linux RDMA user space upstreaming goes, we are targeting a 1.8 release for libfabric. So we'll have a pull request out for that. And I think Sean said it's going to be out in summer. So that's our goal. And like I said, for the upper level protocols in the kernel, we believe we can emulate RC. If you have any feedback, or if you think that you have a clear use case for RC QPair type in the kernel, please let us know so we can prioritize it. Our goal is to get Intel MPA working with EFA by the second quarter of this year. The current performance expectations, you should expect less than 15 microsecond half round trip latency within a placement group. Placement group is a notion of, it's a logical notion that lets you get full bisection bandwidth between your cluster nodes, right? And you can expect like 15 microseconds or less with the OSU latency benchmark. A single QPair or a single endpoint MPA bandwidth is about 70 gigabits per second, and the full bandwidth going out the node will be 100 gigabits per second. And our goal after we launch is to extend the providers that we have to be more comprehensive as far as libfabric capabilities goes and libIB-verbs capabilities goes. So that's all I had. Okay.
How the heck are you going to emulate RC? And does that mean you'll also support RDMA read, RDMA write, and all the other operations that come with RC?
So currently, so the device has semantics of an RDMA-based API, but we currently support only send-receive APIs or send-receive operations. So the goal is to, so our focus is currently MPA and machine learning, right? And we will do whatever it takes to optimize those workloads. And if that involves having to do an RDMA interface, we would go down that route.
There's no reason why you can't emulate RDMA, RC, examples of that.
Right.
There's a lot of the QPair-based RC stuff in software emulation.
All right. I was interested in what his plans were, but okay.
It won't be zero copy, right?
Right.
I don't think so. No.
But like I said, if that's what our customers want, we'll use whatever technology it takes to build it out. Right?
Have you posted the libfabric provider?
For PR, yes, there's a pull request out for the libfabric provider. No, not yet. So depending on how the streaming goes for the kernel driver and the libIB-verbs stack, we're going to talk to Sean and see how to cut out a PR. Yes.
I might have missed it, but can you talk about the status or plans about libfabric level RMA support, like FI RMA or FI atomics?
Right, kind of like the previous question, right? So currently we support just send receive operations. Or, for example, Intel MPA, we're working with Intel, and they use active messages over send receive. and using some capabilities of libfabric to support one-sided operations and Intel MPI, right? Over time, in the fullness of time, if there's a customer need for it, there's nothing stopping us from looking into technologies like zero copy, one-sided transfers to implement FIRMA.
Just a simple question. Maybe I missed it in your talk. What are you speaking on the wire? Is it UDP or is it?
It's the custom SRD protocol that I touched on, right?
So it goes down to the Mac as well. So the whole stack is proprietary.
Yes.
Okay. Thank you.
Have you considered other ULPs or APIs like UCX to abstract your?
No, libfabric is going to be, or the libfabric's over libIB warp stack is going to be the primary mechanism in which you can interact with EFA. Right.
Have you considered others?
I don't think we have. Maybe that's a question for, I'll have to check. I don't think I'm the right person to answer that.
Nice talk, Raghu. So I see you only have MPI level numbers.
Right.
Are you guys planning to support other kinds of data center applications?
Right. Yes, that's totally in our radar, and it is our goal to support most programming middleware, right? And there's nothing, there's no real reason why you cannot. But our focus right now is MPI and machine learning applications with Nickel. But in the fullness of time, you'll see us supporting other MPI libraries, other programming models, middleware, including big data middleware that I'm guessing you're interested in.
Can you elaborate on the congestion control aspect of it?
I think this slide talks about it a little bit, right? So by taking the the ordering requirements out of the protocol, we are able to spray packets across multiple paths in the network, ECMP paths, right? So if, for example, a link goes down, if there's congestion in a particular route, we can work around the congestion in our data center networking fabric, right? It's part of the SRD protocol. There is an explicit congestion control protocol. Yeah. Anything else? Right. Sorry? I don't have graphs. I don't even know if we make those available, but talk to me offline. We can figure it out. All right. Thank you.